rho, or we can call it pressure top, plus rho GH. So we can call this one example 1. So let's talk about, let's say, the pressure in the bottom of the ocean, okay? So the depth of the ocean, it averages about 3,800 meters. So calculate the pressure at the bottom of the ocean and compare with atmospheric pressure. Okay? And then we could do the pressure at the most deepest part of the ocean. The deepest part of the ocean can be about 11,000 meters, and it's in a place called the Mariana Trench, and it's about 11,000 meters. So let's do the pressure at the bottom of a typical ocean, the average ocean. So for typical depths, D is equal to 3,800 meters at the bottom of the ocean. So what would the pressure be? So the pressure would be pressure at the top, which is atmospheric, 1.013 times 10 to the 5th pascals. So we talked about that last time. And then the density of the ocean, if we assume it's a seawater, so it's going to be a little bit more dense than 1,000, right? So it was, based on last week, what we said, it was seawater was 1,030 kilogram per meter cube. So whereas regular freshwater would be 1,000. I'm assuming here again that the density in this one doesn't change as you go down. The density of water stays the same. So you have 1,030 kilogram per meter cube. The G is 9.8, and the G doesn't really change much either over the depth of the ocean. And then the height, for the H here, you put the depth 3,800. So let's see what we get here. 1.013 times 10 to the power 5 plus 1,030 times 9.8 times 3,800. Get this big number here. 3,845,8 458,500. So we get 1. So we have 3. So 38. We could say that in terms of 10 to the 5th, we could say like this: 380. 1.013 times 10 to the 5th. This is 101,000. So the pressure at the sea level is 101,000. 2, 3, 4, 5. 101,300 pascals. This one is a lot more. It's 38 plus 10 times 30, 9.8 times 3,800. So it's 38 million pascals. So in terms of 10 to the 5th, if you want to go back 5 spaces, you got 1, 2, 3, 4, 5. 384.585 times 10 to the 5th pascals. So you get 3 and then 1, 2, that's 10 to the 5th. So if we compare that to atmospheric pressure, this is pressure at the bottom. Pressure at the atmosphere, 1.013 times 10 to the 5th Pascal. and we take the ratio, pressure at the bottom, pressure at the atmosphere, it's going to be, divide this by 1.013 divided by 10 to the power 5. It's going to be 379.65. So we would say 379 bar, or 379 atmospheres. So that's a lot as you go down. Of course, no human can go down that deep. You have to be in a submarine to protect you from that pressure. How about the pressure at the bottom of the Mariana Trench? That would be 11,000 meters. So you would put here for Mariana Trench, you have the depth is about 11,000 meters. So the pressure is going to be 1.013 times 10 to the 5th plus 1,030 times 9.8 times 11,000. So it's going to be quite a lot more even. 1.013 times 10 to the power 5 plus 1,030 times 9.8 times 11, 1, 2, 3. Okay, so I get this big huge number, and then if I divide that by the pressure of the atmosphere, 1.013 divided by 10 to the power 5, I get 1,097.09 atmospheres. So I basically, what I did is I then divided this whole thing by 1.013 times 10 to the 5th. And then this cancel this, and then basically you get 1 plus the ratio of these two. You get 1,097.09 atmospheres. That is amazing how much of a pressure that is. Only the strongest submarines can ever get there. Okay, now let's go do an example 2 for our